Hey y'all, welcome back. Today we're going to start a brand new unit all about vectors. So before today, most units that you've learned about are considered scalars, meaning that there just is sort of this numerical component to it. So for example, you have a measurement of 6 feet or 20 minutes. But today we're going to look at something that is known as a vector, which not only has that numerical component to it, but it also has a direction associated with it as well. So the difference here would be like a speed as a scalar, 10 meters per second, versus a vector which says 10 meters per second moving north. And so there's a lot more information that you can get from these vectors. So by definition, these quantities like force and velocity involve both magnitude, which is the numerical component to it, like how big or long or how much something is, and the direction, which tells you which direction the force or the velocity is moving in. These can't be described using a single value. So to represent these quantities, we use what's known as a directed line segment. And basically what that is it's just a line segment, like, from, we'll say, point P to point Q. And not only are we going to measure the length of this, which is going to represent the magnitude. So maybe I'll make a little note here that length is the same as magnitude. But there's also a direction associated with it. And the way that we notate that direction is with a little arrow. So this directed line segment is basically saying that the vector starts at point P and ends at point Q. This is the initial point and the terminal point. Now, when you have vectors that have the same magnitude in the same direction, they are considered equivalent regardless of where they are on the plane. So if you look at this little picture up here, maybe I'll zoom in a little bit so you can see it a little easier. These are two vectors. One is PQ and the other one's RS. But notice how they're pointing in the same direction and they're the same length. So we say that they have the same magnitude and the same direction, and so we consider them equivalent. Now, so they don't have to be in the same spot. So to sort of standardize how we sketch out vectors, we put them in what is known as standard position, kind of like how we had a standard position for angle measures. So vectors in standard position have their initial point at 0, 0, and that's pretty much it. So PQ, for instance, up here is in standard position, but RS is not. If we put RS in standard position and we move the initial point back to 0, 0, but maintained the magnitude or the length of this and the direction, it would end up terminating at the same point as Q. So this directed line segment can basically be put right on top of this. So we consider those equivalent. Just a real quick vocabulary term before we move on. A unit vector is a vector that has a magnitude equal to 1. So if it's got a length, that's 1. For instance, like if I have this little vector right here, and you can clearly see that the length is 1, that would be considered a unit vector, just like how we have a unit circle. Okay, so how do we actually write these vectors? There's two ways that we're going to write them. One is called component form, which is going to be the one I will be using more often. And then we also have another form called linear combination form. So let's say we have a vector that's in standard position. We'll call it vector v, that we can see in this image. Remember that all vectors, if they're in standard position, start at the origin and then terminate wherever they end up terminating. So this particular one, vector v, is terminating at 1, 3. So the way that we write this in component form is we use these little vector brackets, which are kind of like parentheses, but they're sort of angled like this. And then we write the terminal point inside here. So the way I know if I'm writing this that it's a vector instead of like a coordinate is because I use these little vector brackets here. There are a couple different ways a couple different standard ways that we can write like the names of the vectors. The one that I will most often use will be just the letter with a little arrow over it. Okay, so this is what I'm saying here is that vector v is 1, 3. I know there's a lot of textbooks that will use like just like a bold letter. So like it might be written like that, and that's acceptable too. You can see the textbook that I clipped this little image from is using that sort of bold notation. But I feel like with the little arrow, it just gives a little bit more obvious indication on what the object that I'm naming is. Okay, so that's one way that we can write a vector. The other way is called linear combination form, and I'm going to go into a little bit more detail on like the parts to this, like why we're writing it like this at all. But basically, oh, that's going to be a little too big there. Basically, we're going to have vector v, so I'm talking about the same vector here. And this alternate notation that you can use to write the vector is going to be 1i, the little hat here, plus 3j. And so really what this is talking about, and like I said, I'll come back to this to go into a little bit more detail, but basically it's giving you the horizontal and vertical components. These I and j are representing standard unit vectors, which I'll talk about later, but basically all you need to know is that the coefficients of I and j are going to be the same numbers that you would write if you wrote it in component form. So I will mostly be using component form, but I'm going to throw in some linear combination form here and there. And when we start talking about how to combine vectors using addition, and when I go into a little bit more detail about standard unit vectors, this notation will make a little bit more sense, I think. But we'll get to that before we're done today. So let's talk about how to calculate the magnitude and direction angle of whatever the vector happens to be. So the magnitude is represented in the directed line segment by the length. So whenever I'm asking for the magnitude of the vector, that's like the numerical component too. So if I say I'm moving 10 miles per hour north, the 10 in that description is the magnitude, where the north is describing the direction angle. So to find the magnitude of a particular vector, we are going to look at the length. And so if you have a vector like 1, 3, you can simply set up a right triangle like this. And since we know the side lengths of this right triangle, 1 and 3, we can use the Pythagorean theorem, which is my little hint here, to find the magnitude of vector v. Now, notationally, the way that we'll actually write magnitude is we'll use these bars, kind of like absolute value bars, but there'll be two of them. And we'll say the magnitude of vector v equals. So if you see these double bars around a vector, that is referring to the magnitude, okay? And the way we can compute it is by taking the square root of a squared plus b squared, okay? Or in this case, 1 squared plus 3 squared. And then you would type that in your calculator if need be. Here we probably don't need a calculator. 1 squared is 1, 3 squared is 9, so 1 plus 9 is 10. So we will say that the magnitude of vector v is 10. The direction angle is going to be the angle in standard position if your vector is the terminal side of the angle measure. So let me notate this on our diagram. What we're talking about basically is this angle right here. So to find an angle, we're going to do something that we did a lot last year at various points in the semester, and that is we are going to use the definition of tangent, which, if you'll recall, tangent of theta is the opposite side over the adjacent side. Okay, so the opposite side being y and the adjacent side being x. Okay, now this is the x and y component of the vector. So like in this case, the x would be the 1 and the y would be 3. So one of the things that we talked about a lot last semester is how if we're trying to find this angle measure and I solve for theta here, I'm actually not necessarily getting the theta that I want. This is going to give me the reference angle. Okay, so the reference angle, meaning like this angle inside the right triangle. Let's see here. There we go. Oops. The reference angle is going to be equal to the inverse tangent of the ratio of the y component divided by the x component. Now, depending on which quadrant you're in, we will use the reference angle to find the actual direction angle by doing something a little different. Now, if we're in quadrant 1, and this should be a little bit of a review, hopefully this rings a bell, because this is something that we had to deal with on several occasions last semester. But anyway, if you're in quadrant 1, so if theta is in quadrant 1, then we'll say that theta actually is the reference angle. So, oops. Okay. So, like in this problem, we can just simply type this in and compute this with the calculator and find this reference angle, which will actually give us theta because it's the same angle. Now in quadrant 2, we will have to do something slightly different because the reference angle is going to be the angle between the negative x-axis and the terminal side of the angle. Let me show you a little diagram here to kind of explain what I'm talking about. Just kind of draw this out. So yeah, if you're in quadrant 2, and let's say your vector is over here, then this little formula to get the reference angle is actually going to give you this negative angle right here. And so what we want is this angle right here. So what we would do is we would add either 180 degrees if we're in degrees, or pi radians to the reference angle. So this reference angle will turn out to be negative because of the definition of a reference angle, and because of how we calculate it as well. And so we will add 180 degrees. Now, if you're in quadrant 3, you'll do basically the same thing as if you're in quadrant 2. Just go ahead and copy this. And the reason for that is the reference angle ends up being positive there when you're in quadrant 3. So in quadrant 2, the reference angle is going to be negative here, but in quadrant 3, say your vector is right here, the angle measure that this formula is going to give you is going to give you this one right here. But what we really want is this one right here. Okay, so we'll take this positive angle measure and add 180 degrees. If you're in quadrant 4, you're going to end up adding 360 degrees, or 2 pi if you're in radians. I think most of these should be in degrees though, so that's why I'm going to write these out in terms of degrees. So yeah, in quadrant 4, and let's see if I can squeeze in this little diagram here. I didn't do a diagram for quadrant 1 just because I think it's kind of obvious. But maybe I'll throw it in there too. See if I can throw in see if I can fit in a diagram for quadrant 4. So in this case, if you're in quadrant 4, your vector is going to be pointing like over here. The reference angle that this little inverse tangent formula is going to calculate is going to give you this angle right here, and the angle you actually want is this one. So instead of adding 180, we're actually going to add 360. So this might give you something like negative 45 plus 360 will give you the correct angle measure. So yeah, so this is kind of how you're going to find the direction angle. And so if we're going to calculate the direction angle of this particular example, this is in quadrant 1. Okay, so I'll make a note here that 1, 3 is in quadrant 1. So we can just use this formula directly to find theta. So theta will be the inverse tangent of 3 over 1, and we can compute this with the calculator. So let's go ahead and take that calculator out. So we get the inverse tangent of 3 over 1, and before I hit enter, I'm going to make sure I'm in degrees here. You can leave it in radians, I guess, but degree I feel like gives you a better sense of what the angle measure is. Now, just looking at this picture over here, if I had to guess before I actually hit enter here, I'm going to say if this is 90, maybe that's like 80, maybe 70 degrees, somewhere around there. But let's see what it actually is. Okay, so it's 71 degrees. Okay, so we'll just round that to 72 degrees. All right, so what we've done here is computed both the magnitude and the direction angle of vector 1, 3. These are the two characteristics that describe how much the vector is, or how fast you're going, or whatever the unit. This doesn't have any units, but the numerical component to it, and then the direction angle tells you which way it's pointing. Okay. So that's how you calculate magnitude and direction angle. Magnitude, you can just use the Pythagorean theorem, and then for the direction angle, you'll use tangent, and then depending on what quadrant you're in, you may have to either add 180 or 360 or 0 to actually find the angle measure. So now let's just practice, kind of getting the hang of these vectors. So let's say we have a vector 2, -4. And let's start by sketching it in standard position. Okay, so I'm gonna 2, -4 looks like that's gonna be in quadrant 4. So I'm just gonna have an emphasis on my sketch in quadrant 4. So 2, -4, I'm just gonna say 1, 2. And this is a sketch, it doesn't have to be perfect. 1, 2, 3, 4. So the terminal point will be right here. So when I draw my arrow, I'm gonna start at the origin and point to that terminal point. Just to kind of make this clear, this is at 2, -4. Okay, so there's the sketch. That's all you really have to do there. So the magnitude is going to be the length of this vector, and so the way we calculate that is using the Pythagorean theorem. So the magnitude of vector u, so I'm going to say the magnitude of u, and then this particular problem is using the bold notation for the vector, so I'm not going to put the arrow over it, but I think you'll see on the homework most of the time the way I'll describe vectors with a little arrow on top of here. It's just a notational difference, it's not that big a deal. But anyway, so the magnitude of u will be equal to the square root. Oh, why is that not put in there? Oh, you know what? I'm not in equation form, I don't think. Let's try that again. There we go. So u equals the square root of 2 squared. And then I'm going to write -4 squared here, but normally when I would actually calculate this out, just use positive, because whenever you square something, it becomes positive anyway. Oops. Oh, whoa. That is not what I wanted to come up. Let's try that again. Can I not? Oh, I guess I can't control the, I want this just to say, here's what I'll do. I'll just draw it in. No, it's not going to. Okay. All right, you win, Cammy. All right. Just to make this look a little better, I'll put this over there. I don't know how to make this You know what I'll do to make? I guess I'll just have to do this separate. That's kind of annoying. I know you're thinking, gosh, does it really matter? No, not really, but let's just do it like this. I just want to be consistent about the notation here. All right, well, there we go. That's the magnitude of vector u is equal to the square root of 2 squared plus 4 squared. And so now we can simplify that. Probably don't need a calculator here. 2 squared is 4. 4 squared is 16. 16 plus 4 is 20. So the magnitude of u is root 20. And then the direction angle, we're going to use tangent to find that. Now the inverse tangent is going to give me this angle right here. This is going to be the reference angle that it's going to give me. You know what, let me use a different color just to emphasize it. There we go. So this angle right here is going to be the reference angle. And what we actually want is this one right here. This is going to be the direction angle. So basically we're just stating the angle, giving a positive angle measure for this. So the direction angle of u, we'll start by using this little formula right here, this inverse tangent of y over x. But again, that's just going to give us the reference. And so theta is going to be the inverse tangent of, let's see here, negative 4 over 2. And then since we're in quadrant 4, I need to add 360 to actually get the right one. So now it's calculator time. Okay, so let's pull out the calculator. I've got the inverse tangent of negative 4 over 2. And then I'm going to add 360 to it. So I get about 297 degrees. All right. So that's how you work this whole thing. All right. So let's kind of go back to, earlier I was talking about this whole linear combination way of writing vectors. But to really understand why we can write it like that, we need to talk about unit vectors. So unit vectors are vectors that have a magnitude that's equal to 1. And there are two standard unit vectors on a two-dimensional vector. And what standard unit vectors are they're vectors they're unit vectors, so they only have a magnitude of 1, but they are pointing in directly the x or the y axis. So this little I with this little triangle hat, this little arrow up thing, this is called the standard horizontal unit vector, and what that is just simply 1, 0. J is going to represent the standard unit vector that's going in the vertical direction, so that will be 0, 1. And you can combine these vectors to create essentially any two-dimensional vector. Let me kind of sketch it out just so you can kind of see what these vectors look like. If I can make a straight line here. There we go. So yeah, like this I is really just going to be like a 1 unit long vector in the horizontal direction. Okay, and this J represents a 1 unit long vector in the vertical direction, the positive vertical direction. So it looks kind of like this. Okay, where this is at 1. If you happen to have a 3-dimensional vector, like so you've got x and you've got y and then you've got z kind of pointing in and out, you're going to write those vectors just like how you would write a 2-dimensional vector, except you have 3 numbers instead of 2 numbers. So like these 2 vectors will be the same, but if you have a third one, then you're going to have a like 0, 0, 1. So if you're working in 3 dimensions, your first standard unit vector would be like 1, 0, 0. The second one would be 0, 1, 0. And then the third one would be 0, 0, 1. And really, these are just going to be used to write vectors as a linear combination, kind of like how I did up here. Okay. Outside of that, you know, there are not going to be a whole lot of questions about I, J, and K, but I might write a vector in this form, so you want to know like what it really is. Now these are not the only unit vectors. These are called the standard unit vectors. So let's say we wanted to find a unit vector that is in the same direction as another vector. So like, for example, let's say we have a vector 2, 3. So just to kind of sketch that out, here's 1, 2, 1, 2, 3. Here's where the terminal point should go, and then so the vector looks like this. But you can tell really quickly visually that the magnitude of this vector is more than 1. And so let's say we want to find a vector that is in that direction. You know, maybe it'll be roughly here, that actually has a magnitude of 1. So that's really what this is asking for. Find a unit vector that's in this direction. Now finding this is not so bad. Basically what you want to do is multiply each of the components of your vector by a scale factor to kind of shrink it. So let's say we multiplied it by 1/2. That would put it like roughly here, which is, you can see that's still bigger than 1. So we don't want to multiply it by 1/2. What you really want to multiply it by is 1 divided by the magnitude. So just to kind of keep it short and sweet here, to find a unit vector in the direction of another given vector, divide both components by its magnitude. So in order to do this, we first need to calculate what the magnitude is of this vector. So, so let's go ahead and compute the magnitude of vector 2, 3. This doesn't have a name, so I'm not just gonna arbitrarily give it a name. I'm just gonna call it what it is, which is 2, 3. So yeah, first find the magnitude. That's gonna be your step 1 here. Now this is going to equal the square root of 2 squared plus 3 squared. Remember, we're just really using Pythagorean theorem here. And 2 squared is 4, 3 squared is 9, and 4 plus 9 is, what is that, 13. Okay, so that's the magnitude. So once you have the magnitude, you can divide each component by the magnitude, and then you're essentially done. Okay, so you might be able to simplify or convert it to a decimal. Sometimes it works out to be a nice fraction, sometimes not. But essentially what we have here is the original vector 2, 3, but we're going to divide each one of those by the magnitude, which we found was root 13. And there you go. We could simplify this, but I think more often than not, I'll give it as a rounded number. So let's see what this would be approximately. I'm going to have to pull out the calculator here. I don't happen to know what 2 divided by root 13 is off the top of my head. So 2 divided by root 13 is going to be roughly 0.55555, and then the 3 divided by root 13 is going to be a roughly 0.83 2. Now this is a point on the unit circle. Remember, we're trying to find a vector that is a unit vector, meaning the length is 1. So this coordinate, 0.555, 0.832 should be on the unit circle, or approximately. So that would be your answer. This is going to be the exact answer, so we could put equals, and this would be the approximate answer. And depending just kind of what I ask for, you could write either one of these. Now, this is how we can find, a vector that is a unit vector in the direction of a given vector. But we can take this a step further and find a vector of any magnitude that is going in that direction. So let's say we have this 3-dimensional vector, and I want to find a vector that's going the same direction but has a magnitude of 10. Okay. So to do this, you're going to do exactly what we did before. Okay. So we're going to find the unit vector. So first, find the unit vector in the direction. So to do that, we just you do the steps that we did before. So we got to find the magnitude, then we'll divide each component by the magnitude. Now once we have the unit vector, we can scale that back up. This is probably the easiest way to do this. So second, or last, we will multiply the unit vector that you just found by the new magnitude. So in this case, we would multiply by 10. So let's start by finding the unit vector that's in the direction of 2, 3, 4. And to do that, we need to first find the magnitude of this one. So when we had a 2-dimensional vector, I said, hey, just use the Pythagorean theorem. We did that up here, and actually we've done that twice so far now. So the way that will generalize two vectors that have more than 2 dimensions is very similar. You just sort of add on another something squared. So the magnitude, go ahead and write this. See if I can get that vertical. There we go. Or you know what, it might just be easier to type it. The magnitude of vector 2, 3, 4 will be equal to the square root of 2 squared plus 3 squared plus 4 squared. So I'm not going to give you any vectors that have more than 3 dimensions. So this will be the most you have to do. But even if you had 4 dimensions, you just add whatever that thing squared is. So this is going to be how we calculate the magnitude. And let's see if we can do this without a calculator. And if we get stuck, we'll use a calculator. So we've got the square root of 2. I'm sorry, the square root. 2 squared is 4. 3 squared is 9, and 4 squared is 16. Okay, so I've got 16 and 4 is 20, plus 9 would be 29. So now that we've found the magnitude of this vector, we can divide each component by that magnitude. So if the question we're asking, hey, what's a unit vector in the direction of 2, 3, 4, it would be 2 divided by root 29, 3 divided by root 29, and 4 divided by root 29. I'll just label this. So here's the magnitude. Okay, so we found the magnitude of the vector, and we use that to find a unit vector in that. So basically what this represents is a vector in the same direction as this one, but the magnitude is only 1. And so what we can do is scale this back up so that it has a magnitude of 10. Basically what we're doing is we're taking a vector, shrinking it down so that it's just a unit that has a length of 1, and then multiplying it by 10 to make it the magnitude that we want. Okay, so that's going to be our last step here. Multiply the unit vector by the new magnitude. What we could do here is kind of pull all this together. Excuse my, all right. Let's kind of make this look a little prettier. Oh, nope, didn't like that at all. I'll just have to drag them individually, I guess. No problem. Okay, so we'll take this vector and we will multiply it by 10. Okay, so we would get a vector that is times 10, right? So basically we're going to multiply each one of these by 10, and so 10 times 2 is 20, 10 times 3 is 30, and 10 times 4 is 40. So that would be our final answer there. Okay, this represents a vector in the same direction as this one, but it's got a magnitude of 10. So far we've looked at what a vector is, how do we calculate magnitude and direction, how to find a unit vector in the direction of a given vector, and really to find a vector of any length in that direction. But the last thing we're going to go over today is how, or I think it's the last thing. Yeah, well, maybe not the last thing. I guess it looks like we still have a couple more things. But the next thing we're going to look at is how to combine vectors arithmetically. And luckily, it's pretty easy. So let's say we want to add two vectors, 3, 2, and 7, 5. Algebraically, all you do is just add. So if I have, the vector 3, 2 plus the vector negative 7, 5, all you need to do is just add the corresponding components, and we will get the resulting vector. Okay, this is called the resultant vector when you add them up. And looks like my notation here came off a little bit. There should be a little arrow on both of these. I'm not sure why it looks like that. But basically, you can either write the result like this, like vector u plus vector v, or you can kind of put u plus v underneath just a single vector line here. Either way is fine. They're just two different ways of sort of notating the same thing. But basically how you're going to combine these, like I was saying, you just add the corresponding components. So like I'll have 3 plus negative 7 as the first component, and then the second component is 2 plus 5. So we would get 3 plus negative 7 is negative 4, and then 2 plus 5 is 7. So we'd get negative 4 comma 7. An easy way to kind of organize your work here is, instead of writing it sideways like this, if you just stack them up like 3 comma 2 plus negative 7, 5. Sometimes just looking at it like this can make it easier to kind of process what you're supposed to add. You don't have to show your work this way, but I find that some students find it a little bit easier to organize it this way, and it's just a little bit more obvious like what you're going to end up with. So this is how you calculate it algebraically. Graphically, it's represented like this. So let's say we're going to start with angle U, which is 3 comma 2. And the way you add vectors graphically is what we call head to tail, meaning like the first vector, which is starting at the origin, ends at 3 comma 2. So here's vector U. Okay. And then we will put the vector we're going to add to it, not in standard position. We're actually going to start it where the first vector ended. So since the first vector ended here, we're going to move 7 to the left and 5 up to get to the terminal point of vector v. So we'll go 1, 2, 3, sorry, to the left. 1, 2, 3, 4, 5, 6, 7, and then we'll go up 5. So 1, 2, 3, well, let's try to make these equidistant here. 1, 2, 3, 4, 5. So this next vector, vector v, is going to start here and go left 7, up 5 is going to be pointing up here. And then the resultant vector, so here's vector v, when I add them together, the resultant vector will be in standard position, meaning it starts at the origin, and then whatever point we ended up with, that's what I'm going to point to. So this is going to be over here, u plus v. See if I can make this look like a v. Sometimes with, there we go, u plus v. So if you're trying to figure out, okay, well, where's that point? It's at -4, 7. Okay, because you're adding, the 3 plus -7, it puts you at -4, and then 2 plus 5 more puts you at 5. So you can kind of see that this point right here corresponds to the resultant, or the terminal point of the resultant vector. Right here. Okay, so this is how you can represent it graphically or algebraically, and these should match up. If you try to sketch it out and you're finding that the terminal point is not what you got when you added them up algebraically, then that should kind of throw up a red flag that either you sketched it wrong or that you messed up the algebra somewhere. These two things should always be the same. So that's how you add two vectors. Let's say you wanted to multiply a vector by a scalar, meaning like a single number, so not a vector. Like if I just want to multiply 2 times 6 times -3, this works just how you might suspect it does, which is we're going to use the distributive property and multiply the scalar by each component of the vector. So our result will be, in this general case, c times x, and then the vertical component would be c times y. So in this case, we would multiply 2 by 6 and 2 by -3, and our resultant vector would be 12, comma, -6. Yeah, I guess I didn't need a whole slide for that, but it's pretty easy. So, doing arithmetic, for adding, subtracting vectors, or multiplying a vector by a scalar, it's pretty easy. Now, when we start to multiply vectors together, that is going to take a little bit more explanation, which is why we're going to save that for next time. So we're not going to get into multiplying vectors today, but like I said, we'll hit that in the next lesson. Now, you can use these properties of how you can combine vectors to solve certain equations. So like this one says, now notice these vectors, again, I'm not sure what happened here with the notation. Should be some arrows on here. It's probably just, yeah, I don't know. I don't really have an explanation. Maybe just the way it saved it as a PDF or something, didn't like it. But, so these two vectors are written in linear combination form. So if you're more comfortable like me in the component form, this is equivalent to just writing it like this. Okay, or this next one is equivalent to -7, 5. So just know that these are the same. You don't have to rewrite it in component form like this, but I find it easier. It's just less writing overall to write it like this versus writing it like this. But anyway, so it says let u equal this one and v equal this one, and it says find x if u plus xv, again, I don't know what's going on with this notation. If vector u plus x times vector, this should be vector v. This should not be on top of the x. I'm not sure why it looks like that. Let's just try to make that a little more obvious there. Assuming, find x if this has an I component that equals 0. So basically we're saying that vector u, which is 3, 2, plus x times vector v, which is -7 plus 5, or not plus, but it's -7, 5, equals some new vector where the I component, that's the horizontal component, is 0. And then the vertical component we don't really care about. So the way we'll do this is we are going to basically set up an equation. Since we don't care about the j or the vertical component, we are going to... Sorry, I had a little interruption there. We're back. So anyway, what I was saying is we don't really care about the vertical component because the only condition here is that the I component equals 0, the horizontal. So we're going to set up an equation, really just concerned about the horizontal component, where we have 3 plus x times negative 7, or so we'll say, here, I'll put it like this, but I'll rewrite it here in a minute, and we want that to be equal to 0. So just kind of reformatting this equation to make it a little nicer. Say 3 minus 7x equals 0. And we can solve this like you would in Algebra 1. So we'll like subtract 3 from both sides and get negative 7 times x equals negative 3. And then we will divide both sides by 7 here. Or negative 7. And so we would get x equals 3/7. So usually the equations are not going to be super complicated. You just need to know how to set them up correctly. That's really going to be the biggest hurdle, is knowing how to set up the equation. So if it's not giving you any information about one of the components, you can usually safely ignore it when you're setting this up. Because, like I said, it's not requiring that this needs to be anything. Now, if it said an I component that equals 0 and a j component that equals 5, well, you just have to set up a second equation for the y component, something like 2 plus x times 5 equals, whatever the j component would be equal to. So if we said the j component equals 7, we would say equals 7, we'd solve that, and those two x's would need to be the same. So, so that's how you're going to use these properties of these vector properties to solve an equation like this. So I think that's pretty much it for that. The last thing we're going to do is talk about how to find a vector if I give you the magnitude and the direction angle. It says find a vector that has a magnitude equal to 3.5 and a direction angle of 140. Write the vector in component form and as a linear combination of standard unit vectors. So it's asking us to figure out what the vector is and then write it in both conventions, or both notations. So first, let's just sketch it out so we can get an idea of kind of what we're working with here. I always, as you guys know, recommend doing a sketch to really help you understand what it is we're doing here. So the direction angle is 140, so it's going to be slightly lower than 135, which is kind of that 45-degree mark. So it's saying here's our angle, 140. Okay, and the magnitude is 3.5, so that means the length of this is 3.5. Now, to find, what we really need is we're trying to write the vector, like this, and then also in standard as a linear combination. But what this x, y represents are the horizontal and vertical components of this vector. In other words, we're really just trying to figure out like what coordinate this is right here. So we can use our SOHCAHTOA trigonometric functions to find that out. If we know that this angle is 140 over here, then we can say that the reference angle here, or this angle right here, is 180 minus 140, which is 40. And we can use that with a little right triangle that we can draw here. Wow, that's pretty illegible there. Let me try that again. So this would be 40 degrees. Let's see if we can label this a little nicer. 40. Okay, well that's close enough. So for instance, sine of 40 degrees is opposite over hypotenuse, and cosine of 40 degrees is adjacent over hypotenuse. So the only thing we're missing is like the opposite and adjacent sides. So if we solve for those, what we'll get is that the x component will equal the magnitude of the vector, 3.5, times the cosine of 40 degrees. And yes, cosine is making a big comeback. It wasn't gone for very long. And then the y component is equal to 3.5 times the sine of 40 degrees. So I'm writing this out here, but I think what might be a good idea is just to kind of write out sort of the rule generally, is to find the x component. It's going to be the magnitude times the cosine of the direction angle. Or I'll just, let me do a space. No, I guess not. Yeah, it's not going to let me. I'll just write it like that. Oh, that'll work. And then for the y component, it's the same thing. It's the magnitude times, except we have the sine. Okay, so if we're going to write our, let's go ahead and calculate both of these. Okay, so my x component will equal 3.5 times the cosine of 40 degrees. And then the y component is going to be 3.5 times the sine of 40 degrees. Okay, so we're going to use our calculator to calculate. What else would we use it for? Okay, so we got 3.5. I'm pretty sure I'm still in degrees here. Yep. 3.5 times the cosine of 40 degrees. And then I've got 3.5 times the sine of 40 degrees. So my x component is going to be about 2.681, and that is approximate, so let's be clear about that. And then my y component is about 2.249, rounds up to 2.250. Yep. Okay, so the two ways that we can write this are in component form. We would say 2.681 comma 2.250, and then in linear combination form we would say 2.681 I with a little arrow, and I'm gonna have to go back and fix that, plus 2.250 j. Okay, so this would be the component form, and this would be the linear combination form. All right, y'all. Well, that's it for today. I know we got kind of deep here with the vectors, but that's going to be, we really need to set the stage for the rest of the unit here, and I want to make sure you have a good understanding of the fundamentals and all the vocabulary that goes along with understanding vectors. So hopefully you understand it a little bit better. But as always, reach out if you have any questions or there's something that I was talking about that didn't really make sense, and hopefully I can clarify that for you. But other than that, y'all have a great day, and I'll see you next time.